Okay, guys, I'd like to start our discussion with a collision that might occur where we have a long, slender rod rotated about an end axis. And so as soon as you see that, you should be like, oh, okay, that sounds like one of my moments of inertia. It's going to be pinned at some point. Let's call that point P. And it's at rest on a frictionless pivot on a frictionless surface. So this is kind of like a top-down view. And we have incoming a ball with a velocity directed to the right. We can make up some numbers. Let's just call it velocity v for now. And it's got mass m. So mass m, velocity v, and this is directed to the right. And as you can see, it will collide and strike the end of the rod. And so then a classic kind of question that you would see from something like this is, well, what's going to be the angular momentum of the combined rod-ball system after the collision? And it's clear if the collision is inelastic and the ball sticks to the rod, that the rod is going to have an angular velocity in the counterclockwise direction. And so we know that the angular velocity will be this way if it's frictionless and it doesn't slow down. So how is it plausible then that we have a non-zero final angular momentum? And you know, traditionally, if you looked at that rod and said, hey, it's not rotating, there's no angular momentum in the system, there's only linear momentum in the system, well, then this doesn't work. We can't say that our initial and final angular momentums are conserved. That's not true. Angular momentum is always conserved under all conditions. There are no types of collisions or events where this is not true. So what this creates is a need for us to be able to describe the mass and the velocity of this particular particle in terms of angular momentum. And this is new. It's not hard, and so we can say that the angular momentum of this particle is going to be its mass times its velocity v times r perpendicular, where r perpendicular is the straight line distance it is away from the axis of rotation. So if I were to continue this blue line, we can see that r perpendicular in this case is the length L of the rod that is pivoting in this case. It isn't always the case, but we can see that this is going to be this new value that we're calling r perpendicular. So now we can say that there is a conservation of angular momentum. This particle does have angular momentum, and r perpendicular in this case is the distance away from this line of motion and the axis of rotation. Now we can arbitrarily assign any point in the system. We can say, what is this particle's angular momentum relative to point B? And we would now see that there's less angular momentum given the same mass and velocity about a point that's obviously closer to this line of action here that we're seeing. This r perpendicular, which I'll call r sub b, is less than the initial one that I drew. And so the angular momentum of a particle is a function of what you are defining as the pivot point. And I want to make sure that that's clear, that you can define a different pivot point and the object would have a different angular momentum. So let's actually do a problem like this where we might quantify some of the values and actually calculate what the final angular velocity of the combined bar mass system is. However, before I do that, I would like to add this right-hand rule to a problem like this. And it involves, perhaps not surprisingly, your right hand, since it's called the right-hand rule. And if you take your fingers of your right hand and you wrap them around the axis of rotation in the direction of motion, your thumb will point in the associated vector direction. So right now, you guys are looking at this and saying, well, that's a counterclockwise vector direction. But there's another way of describing this. We could say that the vector direction of this angular velocity is in the positive z-axis coming out of the board. So if I were to draw a coordinate system that is a traditional coordinate system, we're going to have our x and y axis directed to the right and directed up. But I would also have to three-dimensionally articulate a z-axis. That's how I might draw it if I were drawing this as an oblique. But if it's coming into and out of the board, it's coming out of the board, that's the z-axis, and the negative z-axis goes into the board. So it would be appropriate for me to say that the direction of angular velocity of the combined mass bar system after the collision is in the positive z direction. It's weird. It's easier to look at it and say clockwise and counterclockwise, but perhaps from some of the lab work that you've done, where you've sat on the other side of the system, then you understand that clockwise when viewed from one side is counterclockwise when viewed from the other side. And so in order to avoid that kind of misunderstanding, we will use an absolute coordinate system to describe angular direction and other angular quantities. Does that make sense? And are there questions on the idea? What if, in order to kind of ask a follow-up question and get you to exercise this a little bit, what if there was a turntable that looked like this? Actually, you know what? Yeah, this is going to be the top view of the turntable. And, this is like one of those playground toys. And so the system is free to rotate. And somebody comes up to it and pushes it and applies a force to the left. Using this new convention, what would be the direction of the torque that is applied to the system? So we'll take out our right hand. The fingers of our right hand have to wrap around the axis of rotation in the direction of movement, and we could say that this is in the negative z direction. If I orient this in a different way, the exact same arrangement, and we're now looking at the side view of the disk. It's not my best three-dimensional sketch. Where we have an axis of rotation that's going up on the y-axis. This is the x-axis. And so I apply a force this way, pushing it this way, then the direction of my fingers would wrap around the y-axis, and when oriented the disk this way, we would say that the direction of the torque is in the negative y direction. Are there questions on that? Okay, we'll come back to that. What I'd like you guys to do is to take a look at this. Let's go ahead and go back to our initial conditions. And let's say that the ball has a mass of half a kilogram, 0.5 kg. We'll say that its initial velocity is 6 meters per second. And we also need to determine the length L of the rod. We'll say that the length L of the rod is equal to 1 meter. And we'll say that the mass of the rod itself is equal to 2 kilograms. And so the question is, if the rod is on a frictionless axle or pivot, and there's no friction in the system, and this ball hits it and collides inelastically, what will be the final angular velocity of the system after the collision? Let's start with that. I'll give you guys a couple of minutes to do it.